Right, so once again, good morning. Our next speaker today, this morning, is an independent security researcher. He founded the Pasten CTF group, which some of you might know, have heard of, and he has previously worked on OpenIBoot. Please give a big round of applause to Oran Avraham.
Thank you. Can you hear me? Okay. So I'm going to talk about how I hacked eMMC chips, or how I fixed dead Galaxy S3 devices. First, an introduction about myself. Who am I? I'm Oran Avraham, 25 years old, security researcher based in Israel. I'm currently working at a startup called Medigate. However, this talk has no connection to my employer whatsoever. I previously worked on OpenIBoot, which was an open source alternative bootloader for Apple iOS devices. We aimed to boot Linux on iPhone 3G, 3GS, and iPhone 4. We had some success. I also found vulnerabilities in the early iPhone basebands, which were used to unlock SIM-free these devices. And I'm also a CTF player with the Pasten team. We're playing tonight, so yeah, good luck to us. This is my contact info. If you want to reach me, you can find it on my website, and there's also my Twitter username. Okay, so an outline about this talk. I'm going to start with an introduction about the story, how I got to hack eMMC devices. Then we'll talk about Samsung's eMMC patch, which they used for Galaxy S3 devices. And then I will talk about how I obtained such firmware and the firmware of these eMMC chips and analyzed it. We'll cover the bug itself that was in Samsung Galaxy S3 devices, and then I'm going to talk about how do we resurrect dead devices, like bricked devices. So let's start with the introduction. This phenomenon was called sudden death syndrome. This was the name that they gave it over forums. And it started in 2012. Samsung Galaxy S3 devices just started dying with no apparent reason. You could use your phone, and then one day it will get stuck. And if you try to reboot it, it won't boot anymore. The phone is basically a brick. And if you're lucky, the phone will boot into the bootloader, so you'll see a loading screen, but it won't boot Linux or Android. And if you're not lucky, then it's just a brick. You can't use it. You can turn it on. If you plug in a USB cable, you'll see nothing. You can't even charge the battery because the actual charging mechanism isn't powered on. So yeah. And there were a lot of rants in forums. So this is an example. Somebody said, this is happening to a lot of people. I hope Samsung do something about this. And actually, they did, but it wasn't like a proper fix. And we'll talk about it later. So let's talk about how do you diagnose such devices. So this is a working S3. You can see the beautiful background, and everything is powered on. And this is a dead one. Yeah, the screen is just black. You can't do anything. Actually, as I said before, if you're lucky, you'll see this screen, which is drawn by the bootloader, which is called Samsung S Boot. And it won't boot. This is the last screen you'll see. And if you press a specific combination of keys, you'll get this screen, which is called download mode, and we'll talk about it later. So this is my understanding. This is my current understanding on how S3 works. So this is a rough schematic. There's a lot of different peripherals that aren't there, but obviously. There's the main CPU, which is called Samsung Exynos. It's an ARM-based CPU. And then you have the eMMC chip, which is a storage device. It's the standard storage device for phones. And there's some NAND flash inside of it. So it's one package. And if you inspect the silicon, you'll see a NAND flash chip. OK, so then Samsung dropped the patch. And what happened is that they said to the press that they just fixed this bug. And since the Linux is GPL licensed, they had to publish the source code. So the patch was called soft patch movinand VTU 00M eMMC failure. And they modified the file responsible, the code responsible for communicating with eMMC devices. So in order to understand this patch, we have to talk about what is eMMC. And so what is eMMC basically? So it's the de facto standard storage for phones. Actually nowadays, high-end phones are starting to use UFS, which is the bus that replaces eMMC, but the majority of phones still use eMMC. And if you can think about it as SD card in BGA form. So it's a package that you can solder onto a PCB, and it's basically an SD card. It uses exactly the same bus. And as you can see, some company called Hardkernel made a PCB which have an eMMC chip soldered onto it, and they made also an adapter which you can plug. And there's no logic to this adapter. It just turns the eMMC into an SD card device. And it works. So eMMC is essentially an NAND flash chip with convenient bus, which is the same bus as SD cards. So for this reason, some people also call this an internal SD card or something like that. And if I'm going to say card later in my talk, I'm going to talk about the eMMC chip. So when you communicate with the eMMC bus, you send commands to the card, and there are 64 commands, and they are denoted from command 0 up to 63. And for example, you have command 17, which is read single block, and command 24, which is write blocks. And each command takes a single 32-bit argument. So you send a command, it has a number and an argument. And all the commands are categorized into classes. And there's one specific interesting class, which is class 8, because if you look at the specification, you'll see that commands 60 up to 63 are reserved for the manufacturer. So if something interesting is going to happen, it will probably happen with these commands. So let's go back to the patch. So Samsung said they fixed the bug, right? So S3 devices shouldn't get bricked anymore. And this patch actually, the first thing it does, it compares the card's name to VTU 00M, which is the hardware revision of the faulty chip. And then they compare a number to the value F1, and this is actually the firmware version of this chip. And then they call a function which it's called MMC start movie smart, which isn't that interesting, so I'm not going to talk about. And if all these comparisons are true, then it will call MMC start movie operation, which is the main logic responsible for fixing the chip. And the thing to note about this patch is that this code runs every time you boot the device. So every time the eMMC chip is powered on, this code runs. Okay, so let's talk about MMC start movie operation. So this is, I edited the code for brevity. It's not the exact same patch, but this is basically the logic that they use. And this is very interesting. There's one strange thing about this function. There's MMC movie erase command, and erase is an MMC command which takes two arguments. It uses two arguments because you precede it with a different command, so you can give it two arguments. And the first argument is the start block number to erase, and the second argument is the end block number to erase. And it erases all the blocks in between. So what should happen is that the first call to this function should erase all the blocks starting with 4300 up to block number 4A03B510, right? This doesn't make any sense. And then the next call is that the ranges overlap, and this was very strange. So my guess was that this is probably not an erase command. It is probably something else somehow. And the next thing to note about this function is that you see The first two calls are MMC movie CMD, and the last two calls are also to the function MMC movie CMD. And MMC movie CMD is basically command 62, which is a class 8 command. So it's reserved to the manufacturer. And my guess was that the first two calls basically enter some secret backdoor mode that Samsung hid inside the eMMC chip. And the last two calls leave this mode. So when you're in this mode, erase command doesn't do erase anymore. It does something else. And then I saw that if you inspect the first argument, you'll see that the numbers are consecutive. They increment by 4, except for the last number. But all the first 5 numbers are consecutive. And the next thing, so it looks something like memory addresses, right? And if you look at the second argument, I noticed something very interesting. If I assumed this is memory data, then if you look at it like as little endian numbers, you'll see 10b5. So it starts with 10b5. And I used to code a lot of ARM assembly. And 10b5 is push in thumb. And thumb is an instruction set from the ARM specification. And functions in thumb start with push, right? So this is an eMMC next to a thumb. And basically, this is my current understanding of how eMMC works. So you have this all eMMC chip, but there's not only a NAND flash inside of it, there's also a microcontroller. And in Samsung's case, this is an ARM-based microcontroller, which contains some firmware. So I thought this patch might modify the internal memory of this chip somehow. So what I wanted to do is to examine what this patch does. So I just took all this data that it writes and put it into a binary file, which I called patch.bin. And this is, I just used IDA to see what is going on there. And this is Samsung's patch. So at the bottom, you can see the actual thumb instructions. But if you're not familiar with thumb, you can see also a C-like pseudocode. And what they do is basically they call a function, and if it returns 0, the chip will go into an infinite loop. And this is interesting because later on I understood that what was there before this patch, it was just a call to this function, and there wasn't this check. So they took a single call to a function and turned it into a call to the same function, but if it returns 0, they just go into an infinite loop. So my thought was, this can't fix anything, right? Because the chip is either going to do the same thing as before, or it's going to go into an infinite loop. And then I read some threads over forums, and I saw this thread, Ultimate Galaxy S3 Unusual Freezing thread. And this is a quote from the actual thread. You can see that Galaxy S3 is freezing with lockup, screen not responding, ending up with unusual rebooting and boot looping, and angry S3 users reporting this problem, and it keeps freezing every 5 minutes or 50 plus freezes a day. This is insane, right? This phone is not usable. I can't use it as my phone if it freezes every 5 minutes. And I had an S3 back then, and I started observing freezes in my phone as well. So the next step that I wanted to do is to obtain the eMMC firmware in order to understand how it works. So how do you get a firmware? The first way to do it is to write. So I can write the eMMC's memory, right? So I can just write code to random locations, and hopefully it will get run somehow. And then just write things to different addresses and do lucky guesses, and maybe I will see something on the eMMC bus and then try to obtain the firmware, but this is like a shot in the dark. So the next thing I thought about doing is to fuzz different commands, like use command 60, 61, different class 8 commands. But I didn't want to destroy my own eMMC, which was still working. So the last thing I thought about doing is to look for clues. So how do you look for clues? I just Googled these numbers that Samsung used to enter this backdoor mode. And I saw a different patch. So this is a patch from a different device, and it's called patch the firmware of certain Samsung eMMC parts to fix a bug. And it uses the same mode as before. So notice that they use arguments EFAC62EC, and then it's 1021 and 4 zeros. And this is important. So they use 1021, 4 zeros, right? And then they write the value FF to the address for the D9C. But then there was something else afterwards. So if you continue to read this patch, you'll see this thing. This is a snippet which is enclosed by ifdef, which is called test MMC firmware patching. And they use the same EFAC62EC as before, but now they use the argument 1021.0.0.0.2. And the next thing is that they use an erase command with the same address as before, but then they do a read command, right? And I was wondering, this might be Samsung's way of reading the memory address of the memory of the eMMC chip. Because they use an erase command with the same address as before. The second argument is 4, which looks like a size. And then they read a D word from the eMMC. So I took this snippet of code and modified it into this snippet of code, which basically just loops over all the addresses in the address space. I just guessed how big the address space is. And I just read a single D word every time and dumped it into a file. And then I got this thing, which looks like a firmware, right? The names aren't the names that you see, like are NMI and Hardfault. These are my names. What I saw was addresses, but this looks like a thumb vector table. So I understood that I basically got the firmware of my own chip. So the next step was to reverse the firmware in order to analyze what the bug is. So luckily for me, the firmware contained strings, so I can use them as part of my reversing process. But actually, it contained a string, a single string, and it was this string, which isn't very useful if you're trying to reverse a firmware. And as you can see, this is a snippet of my reversing process. I used a lot of names, flip bit in somewhere, and memory mapped IO, 1,000 2D words, or but I basically understood the high level logic of this code, and I got to the point in which I can understand most of the firmware. So let's talk about the bug. Before we talk about the bug, we have to talk about what is eMMC exactly. So let's talk about normal storage first. This is like hard drives. You have two operations which you can do. You have a read operation, which reads data from the device, and then you have a write operation, which writes data onto the device, right? This is pretty normal. Then you have NAND flash storage. So if you have a NAND flash storage, you can do a read operation, which still reads data, and this is as before. But write operation actually turns off bits. If a bit was already 0, it won't turn it into a 1. So this is basically applying a mask to bits on the storage. And then you have an erase command, so you gotta have some way of reversing this process. An erase operation erases a whole erase block. It turns all the bits in this block into ones. But it is a slow operation, and there's another problem. Erase blocks have a limited program erase cycle. So if you issue something like 1,000 or maybe 10,000 or 100,000 erases, the block will eventually die, and then it's not usable anymore. So some software have to do this translation, right? To take this awkward storage and do an abstraction which will show it like normal storage. So this is called an FTL, or Flash Translation Layer. And this is common. And the FTL is responsible for many things, but some examples are well leveling, which is spreading out erases among different blocks, so no single block gets erased a lot of times. And then it also does bad block management. If block already died, then it will remap it internally to a different block. It actually have spare blocks. And then the firmware in Samsung's case is also responsible for the eMMC bus communication, or some of it. So what is the bug exactly? So when you do write operations on the device, the FTL has to save some metadata for itself because it has to keep track on how many times this block was erased and what is the internal mapping and so on. So it has some metadata that it saves for itself. And when you do write operations, it has to modify this metadata. And the actual bug was a miscalculation in this code, which not always, but sometimes made the data corrupt. And once it happened, it should only happen once. If the data got corrupted, this is before Samsung's patch, every time you try to power on the eMMC chip, the FTL will try to parse this data, and it's corrupt, so it will raise a CPU exception. And the default exception handler in Samsung's case is just an infinite loop. So you use the device, and one day the metadata gets corrupted, and then you try to turn it on, and it tries to parse the metadata, and it's corrupt, so it throws an exception, and then the eMMC goes into an infinite loop, and you can't access it anymore. And the eMMC is basically essentially dead because you send commands into it and nothing responds, because the firmware is the software that is responsible for answering eMMC commands. So Samsung's patch was something about this, something like this. Right before the metadata is about to get corrupted, halt the CPU. So there's no bug, right? Right before the bug is about to happen, just halt the CPU. So it never happens. And this turned like sudden death syndrome into sudden freeze syndrome. So I wanted to fix my own device. So a quick recap, I got the eMMC firmware by analyzing Samsung's patch. The firmware had a bug causing FTL corruption. Once it happened, the chip won't boot anymore, and Samsung's patch was to avoid the bug happening at all. So the next step is obviously to resurrect dead phones, right? Yeah, what? How do I? So the eMMC gets into a loop at boot. But what happens before it gets into this loop? So I took a look at the firmware, and I saw this memory layout. As you can see, at address 0, there's something that I called a Bootrom. And it's a ROM. You can't write into it. And it is a code. And what it does, it initializes the eMMC hardware, and it loads the firmware from the NAND flash chip itself. And this is strange, because if the Bootrom is already there, why doesn't it already doing the things that the firmware is responsible to do? So my guess was that the firmware was too big to reside wherever the Bootrom resides, so they had to like bootstrap it from the external NAND flash. And then it also has its own machinery for eMMC commands, which is strange because all it has to do is just load the firmware, right? So my guess is that during the production process, the NAND flash is empty and there's no firmware. And then when Samsung produces these chips, they plug them in and there's no firmware. So the Bootrom goes into some kind of recovery mode, and it exposes an eMMC bus, and from there you can write your new firmware. And the Bootrom is basically a stripped down firmware. There's no FTL, but it looks like the firmware itself. And this is my current understanding about how S3 works. So inside the eMMC, you have two silicon dies. The first is an ARM chip, which has a boot ROM, which loads the firmware from the external NAND flash and then boots it. So if we could ever talk to the boot ROM, this might be interesting because we could maybe do something interesting. But the firmware loading actually succeeds because the firmware is still intact. The boot ROM will try to load the firmware is still there, and it will jump into it, and the firmware executes and goes into an infinite loop. So there's no chance of ever talking to the boot ROM, right? Though actually not. This is not correct because on boot, and there's this function at address 7dbc, and a timer is being set for 35 milliseconds. And if during this time period some interrupt fires, this is interrupt number 7, I don't know what it is yet, they read a value from a memory mapped IO address, and they compare it to this constant magic. And if this comparison is true, firmware loading is skipped, and it goes right into this recovery mode. And my guess is that, so this is a schematic of the boot process, and the left column is the normal boot process. And if we ever get to the right column, that we will get into this recovery mode. So my guess is that this interrupt number 7 corresponds to some eMMC command. And this value that they read from memory mapped IO is probably the eMMC argument because it's 32 bits. So dead eMMCs get stuck on boot. So this is if the chip is already dead. However, right before it gets stuck, there's a time window. And during this time window, if you somehow trigger this interrupt, the boot process is aborted, and it goes right into eMMC Bootrom recovery mode, which is interesting. But the phone is already dead. How do I even talk to the eMMC chip? So I could have used the hardware mode, like desolder the eMMC and send commands externally, but I wanted to do something with software because I don't know how to desolder VGA chips. So the next step is to talk to the eMMC by some kind of magic, and then we'll access the eMMC Bootrom, and then we can repair it from this Bootrom recovery mode. So I said that if you're lucky, you'll get this screen. So this is the phone's bootloader. This is SBoot, and it is saved on the eMMC chip itself. So how do you get this? If the eMMC chip doesn't respond, how the main CPU gets to execute this bootloader? So apparently, if you read Samsung's specification, you'll see that their eMMC has two partitions, and it's not a partition in the file system sense, it's a partition in the eMMC sense. And there's a boot partition and a user partition. And the boot partition holds SBoot in Samsung's case, which is the bootloader for the main CPU. And the user partition holds everything else. So it stores Linux and all the Android file system and all the apps and etc. So the boot partition has its own FTL metadata, and the user partition also has its own metadata. A friend of mine had a bricked S3 which does load SBoot, so he gets this screen. And what I understood that happened is that only the user partition metadata got corrupted, so the boot partition is still intact. And I suspect this is a common scenario because when you write to your device, you usually don't write to the boot partition, you write to the user partition. So if something is about to get corrupted, it probably will be in the user partition. So this is how S3 breaks. The main CPU will power on, and it will try to access the eMMC and ask, give me SBoot, and the eMMC parses the boot partition, and it will return SBoot to the main CPU, and then SBoot will try to access the user partition in order to load Linux, and then the eMMC tries to parse the user partition metadata, and it's corrupt, so it goes into a loop. So SBoot actually has a device firmware upgrade mode that is called download mode, and there's a protocol over USB. The phone side is called Locky, and the computer side is called Odin. I guess this is a reference to the Norse mythology. And there's no way of sending low-level eMMC commands. So if you ever saw this screen, this is Odin software. It's a software made by Samsung to talk with this protocol. And in this protocol, you can't send raw eMMC commands to the eMMC chip. So I need to send commands to the chip, but the code isn't there in SBoot. So obviously, the thing that I have to do is to exploit SBoot, right? And run my own code. So this is taken from USB PIT packets handler from SBoot. This is a C pseudocode that I wrote. So you control this variable isDump, and if it's one, it will read something from the USB packet that you sent to it, and then it will give you a buffer, and it will use this number that you gave it as an offset to this buffer, but it doesn't do any boundary checks at all. So this is our out-of-bounds read vulnerability, right? And then the second case reads a size from the USB packet, and then it reads it into this buffer, which is constantly allocated on the heap. It's of size 2000, but it doesn't do any boundary checks at all either. So this is a heap overflow vulnerability, right? So eventually I found out this is not actually a 0-day. If you take like an S8 or S7, these two vulnerabilities are fixed. But for S3, which is end of life, these vulnerabilities are still there. So if you have an S3, you can use it. So let's talk about Samsung, the SBoot heap implementation. So if you wanted to allocate some size, and the heap chose to use a chunk which is larger than the size that you wanted to allocate, it will split it from the end. And we'll see an illustration in a moment. And the thing to note about this heap implementation is that there's no security mitigations at all. It's very basic. So let's say that you wanted to allocate 50 bytes, and the chunk that it chose was 100 bytes, then it will give you this part, which is the bottom part of the buffer. And the buffer, the chunk header has a size number, a size parameter, and it will use this size to go to the end. So I wanted to achieve write what were in order to exploit SBoot, and I exploited this chunk splitting technique. So the first thing to do was to fake a chunk header, which I can control with some large size, so it will get split. And then I had to figure out its address, and I can do this with the first vulnerability, the relative read. And then the next step is to make sure this chunk is actually selected when you call malloc. And then it will try to give you the bottom part of the buffer. So it will start from the chunk address, and then it will go all the way to the bottom, which is adding chunk size. And then it will go back the size you wanted to allocate, right? And we want to control this number, and we can control this number. So if I just turn around this equation, if I want to control address, I can just use this number as the chunk size, and then it will give me this address. So the actual details, in my opinion, are boring. So you can find the exploit under this repository. It's public, so you can just take an S3 and use it. And this is a demo. This is download mode, and this is hello world SBoot exploit, right? So it works. Okay, so what if it's really dead? What if this happened, right? What if also the boot partition is gone? So obviously something has to talk with the eMMC and load SBoot, right? So there's also another piece of code which is called Exynos Bootrom, and it resides in the main CPU. And what happens normally is that the Exynos Bootrom starts, and then it loads something which I call the first bootloader, which is prepended to SBoot and is signed, and it just verifies the signature of SBoot and then jumps into it. So you can just think about it like it's together with sboot, and then sboot loads the kernel. But the bootrom has to load the first bootloader and sboot from somewhere. So what does it try to do? So it first starts with the eMMC, but if this fails, it goes to the external SD card. So I just took sboot and the first bootloader and dropped them onto an SD card, but that didn't work because sboot boots into, in this case, sboot boots into SD card mode, in which there's no USB protocol, so you can't exploit it. And as I said, it is signed, so I can't patch it. But apparently some people over a forum, the nicknames are Adam Outler, Rebellos, and RaddeV, they found out that there's a development board called Odroidx, which uses exactly the same CPU, so it's the same bootrom, which uses the same signature, but it uses a different first bootloader, which doesn't do any signature checks at all. So if you take this first bootloader and append to it a patch test boot, it will jump into this patch test boot. And then you can just exploit it and run your code. And this is the modified boot process. So you start with Exynos Bootrom, you plug in an external SD card. The external SD card has Odroidx first bootloader, which is signed, so the bootrom will jump into it. And then the first bootloader will jump to the patch test boot, and then you can exploit it and run your shellcode, and no hardware mode is required at all. So if the boot partition is still intact, the phone loads sboot, and it's stored on your eMMC. But if it is corrupt, the phone uses the external SD card. And either way, I can load sboot, and then I can exploit a vulnerability to gain a code execution on sboot. And the next step is to access the eMMC bootrom. And as I said before, I need to trigger this interrupt number 7 and send this argument somehow. So I just iterated over all the possible eMMC commands, which is from 0 to 63, and I powered off the eMMC, powered it back on, so the boot process gets started again. And then I quickly sent command X with this argument, and I waited some time for the boot process to finish. And then I sent any command which is supported by the bootrom recovery mode, and I checked if I got any response. And I said, this is, maybe it's going to work, maybe not. And then I tried command 0, and it failed. And I said, it's never going to work. And then command 1 worked. So this was very exciting for me, because this is the first time the eMMC actually responds. And up until then, on the brick device, I tried to send several commands to the eMMC, and I never saw a response. And this is the first time I actually saw a response back from the eMMC. This was very, very exciting. And the eMMC bootrom even has command 62 and all this backdoor mode. So let's fix it, right? Let's repair the eMMC. So there are 2 revisions of this faulty chip. The first revision uses firmware F1, which is buggy. And then there were phones with firmware revision F7, in which the bug never occurred. So probably Samsung fixed the bug in later hardware revisions. So my goal was to update the chip to firmware F7 and format the FTL metadata so the corruption is gone. Okay, so what I did was to write a dump tool, a firmware dump tool, which is a kernel module. And then I had to convince anybody over the internet to run my code, which sends low-level eMMC commands on their own device. And thanks to Artesia, which was courage enough to try it, I got a dump of firmware F7, and it worked. And now I just had to write it to the eMMC itself. So this is absolutely doable, because I could have used the memory write backdoor to write my own code and access the NAND flash chip and write a new firmware. But then I found out something simpler. So there's another backdoor, which is command 60. And it has 2 firmware upgrade modes for some reason. So the former mode, which is CBAD1160, supports FTL metadata format. You can send an erase command, and it will format all the FTL metadata. and then you can write a new firmware, and it will do everything for you. So how do I fix a dead S3? I just get the dead S3, which should be. This is important to note that there are there's different revisions of Galaxy S3. I'm talking about GTI 9300, which is the international version. Boot to S-boot, either directly, if the boot partition is still intact, or by using an external SD card. Then exploit S-boot to run your own code. From the shellcode, reboot the eMMC into Bootrom recovery mode. And then use command 60 to format the FTL metadata and flash the new firmware, F7 firmware. Then reboot the eMMC so the firmware loading so the firmware boots. And then you can write S-boot to the eMMC's boot partition. And there's another step, which is to profit. And this means it's demo time. So I pray to the demo gods that it's going to happen. It's going to succeed. So yeah. Okay. So I have a brick device. I bricked it on purpose. This is the device. If I try to turn it on, there's a battery inside. Nothing happens. It's bricked. If I try to get into download mode, nothing works. And I have this external SD card, which does have S-boot, as I said before. And if I plug it in, and I try to boot device, it should boot into. Okay. Yeah, okay. So it boots into something, and now I can use, just go back to the, yeah. And now I can plug it into the USB, and S-boot answers. And now I'm going to run a shellcode which fixes the eMMC. Yeah, it's retrying, it's okay. Yeah, shellcode started. It's rebooted the eMMC into Bootrom mode, and now it will write the new firmware. And it should take a couple of seconds, so hold tight, as it said. Okay. Yeah, so the next thing it's going to do is to reboot into the firmware and then change the boot partition size. So there's actually a boot partition. Yeah, and now the shellcode is done. And I can just use a different SD card, which loads S-boot normally, and it goes into SD card mode. And in this SD card mode, it will write S-boot to the boot partition. So let me just yeah, okay. So this is SD card mode. I think you can't see, but if I now remove this SD card, right, and just reboot the device, so the battery is outside, and now it's yeah. It should boot into yeah. So this is S-boot. So the device is fixed. Thank you. Conclusion. A few shout-outs. So Rebellos, Adam Outler, and Radekdev did all the Exynos U-boot, first bootloader, Odroidx work. So thanks to them, if it weren't for them, I couldn't boot bricked devices. Entropy 512 was involved in the eMMC research back in 2013. And Bunny and Xobs held a wonderful talk here at CCC some years ago. And they talked about hacking Chinese SD cards, and they mentioned my research, and this motivated me to complete it because it was still in progress. So this is the reason for which I'm talking today. So thanks. So I can basically own Samsung eMMCs. I can fix bricked S3 with just software. And in my opinion, this is just a use case, because now you can do interesting stuff with your eMMC chip. And what I think we should do next is to look at newer eMMCs, which I suspect still has this backdoor, because I tried some chip which I could get my hands on, and it had this backdoor. So maybe even the new ones also has this mode. And then there's UFS, which is the bus which replaces eMMC, and it is based on SCSI. And Samsung also produces UFS chips, so it might be wanting to see if there's a similar backdoor. And it's also interesting to look at different vendors of eMMCs, and maybe one day write an open source alternative firmware for these devices. So this is question time. You can find the code that I wrote to experiment with these devices over the following links, and you can find the slides in the bottom link. It's already public, so go ahead. And if you have any questions, this is the time. So thanks.
So thank you very much, Owen, for a really interesting talk. If you have questions, there are 2 microphones in this aisle, and then 2 on the sides. And first question from microphone number 2.
Yeah, hi. Okay, really amazing what you did. Did you have any feedback or contact with Samsung about this?
Yeah, so I published my research back in 2013, sorry, over forums, and I didn't use it from a security perspective. I wanted to fix S3. They never responded, or they didn't contact me in any way. I didn't contact them about the Bootrom recovery mode, because in my opinion, it's not a security issue, and it can be fixed. It can be fixed. And regarding the S-boot vulnerabilities, there's no. It's already patched. So no, the answer is no.
So the way I understand is, this is the only way to actually fix some of the phones that are broken out there, right?
Yeah, I don't know any other way to do it.
Okay,
so, yeah.
Thanks.
Microphone number 1.
After seeing a real-life FTL, do you still use SSDs?
Sorry?
After seeing the code of a real-life FTL, do you still use SSDs or other flash devices?
Yeah, this is a good question. It's okay. And I don't. There's no alternative, right? So, but we might make something. So, yeah.
Number 3.
Do you have any? Do you have any idea what other devices have this model eMMC and like support the same commands that let you access the firmware? Because there's other devices that have had bad MMC.
Oh, okay. Yeah. So the Galaxy S2 had a similar bug, and Kindle Fire, I think, one of their versions. And some of them got patches by Samsung, and it usually was something like this, like patch the internal memory every time the device boots, so the bug never happens. I think in the other devices, the bug was actually fixed.
But are you aware of any non-Samsung devices that have Samsung MMCs in them that might be the same MMC?
I'm sorry?
Are there other devices that aren't Samsung phones that still have Samsung parts in them?
Yeah, so there's not a lot of eMMC manufacturers, and Samsung is a big manufacturer, so a lot of different phones and devices use Samsung eMMCs. So yes, this is relevant to non-Samsung devices.
Number 1.
Hi, thanks for your amazing talk and research. 2 questions. There's the Samsung Galaxy Note 2 that has more or less the same bug. Does your fix and your research also apply to that device? And is there a way to do a chip-off dump without erasing the FTL and contents of the card?
Yeah, so this is a good question. So the first question was, does S2 has the same bug, right?
The Node 2.
The Node 2. I don't know. I never had a Node 2, so.
Okay, I have one that is bricked that way.
Okay, that'd be interesting to try. Yeah, sure, let's start. And regarding the second question, so my code actually formats all the FTL metadata, which is not that good because it erases all this information about how many times every block was erased. A more proper fix would be to actually fix the corrupted metadata, but I haven't got to the point in which I can fully understand the inner workings of the FTL. So this is my current code, but you're welcome to try to improve it.
Wonderful.
Yeah. Microphone number 2.
I'd like to know what the time frame was from you starting to work on the issue till you had the first fixed S3.
Yeah, so I obtained the firmware back in 2013, and I had a working device, and I didn't want to do like bad stuff to it, so I stopped back in this year, and then last year a friend of mine said that he has a bricked S3, so I said, let's try to fix it. So I think if you accumulate the time, it's probably going to be like the time frame which I actively worked on this was something like a few months, probably 4 or 5 months, but it started back in like 4 years ago, and I finished it something like a couple of months ago. So,
cool.
Yeah.
Thanks.
Number 1.
Do Samsung SD cards have the same undocumented commands?
Yeah, I suspect they do, some of them. I actually bought some Samsung SD cards, and they had controllers made by Silicon Motion, but I read over the internet that some specific cards, I think it's Evo Plus, have Samsung controllers, which should have the same vector. So I'm trying to buy one, but as soon as I find out, I will probably post about it.
Thank you.
Number 3.
Hi, thanks for the great talk. So I'm still using an S3 as my everyday phone. So what actually happened a few months ago is that it broke down. But so I still saw the Samsung bootloader, the S-boot, what he described, and afterwards it got stuck at the boot screen from the OS. So in my case it was CyanogenMod, but also when I flashed on something else, LineageOS or the default Samsung's firmware, it still got stuck. So I really had to reflash everything, and then it worked again. That somehow sounds really similar to the bug you described, but in a way it doesn't. So
yeah.
Do you think it's the same thing?
So if it's related, my guess would be that your device have this in-memory patch, which freezes the eMMC. And when you used LineageOS, or what it was before, this infinite loop triggered at some point in the boot process, so the device actually froze before it got to boot Android. But then when you reflashed it, somehow the internal block mapping got changed, and now it doesn't trigger this freezing. But if your chip is a VTU00M and its firmware is F1, then you definitely have the bug.
Okay, thanks.
Yeah.
Number 1.
Hi, thanks for the great work. One question, you said you upgraded the firmware of the eMMC with a newer revision. Are these firmwares actually signed, or can you flash anything on the eMMC controller?
You can flash anything, yeah. They
Okay,
have a simple heuristic which checks if the stack address is, it looks normal, but other than that it just boots every firmware you'll give it. So. Yeah, I think in newer eMMCs, which is eMMC 5.1, there's a mechanism of flashing new firmwares, and I think it should be signed, but I don't have a newer eMMC, so I don't know about it. But yeah.
Thank you.
So I have one last question about the Samsung patch. You said that it basically goes into some sort of infinite loop, but do you think they might have tried to do some busy wait, or are they waiting for something to happen?
No, I think they just want the bug to never happen. So yes, my phone froze a lot of times, and I waited like, I don't know, 30 minutes, and the code in the Linux kernel doesn't do anything, and the code in the eMMC firmware doesn't do anything, so my guess is just waits forever. And, yeah.
So I see there are no questions. So again, big round of applause to Ovan for great work. Thank you.